Welcome along to another Enfield Physics Does a Difficult Question, this time on electricity. You can see we have an EMF of 12 volts and internal resistance of 1.5 ohms connected to two load resistors in parallel. So the first part of this question is show the potential difference across the internal resistor is 6.3 volts. So we start by reminding ourselves, of course, that V equals IR. And we can see that there are 4.2 amps flowing through the 1.5 ohm even resistor. Therefore, we can say that the voltage across that resistor is going to be 4.2 times 1.5, which amazingly is 6.3 volts. A part 2 says calculate the PD across the 2 ohm resistor. Well, what you've got to realise with this is that the 1.5 ohm and the 2 ohm resistor are effectively connected in series along with the cell. Therefore, whatever voltage is across both of those resistors has to add up to 12. Therefore, V, as I've illustrated here, is going to be equal to 12 volts, take away 6.3, which is 5.7 volts. Part 3. Calculate the current through the 2 ohm resistor. Well, we know that it has 5.7 volts across it, and we know that its resistance is 2 ohms. This leads us to 5.7 over 2, which equals a current of 2.85 amps. Part 4 asks us to determine the current in R. Well, we know we have 4.2 amps coming down the junction, and we know that we have 2.85 amps going along the 2 ohm resistor line. Therefore, we can work out what the current through the R resistor is by subtracting these two, and then we get 1.35 amps. Now we can calculate the value of the resistance R. We know that the voltage shown on the diagram across that resistor is equal to the voltage across the 2 ohm. Therefore, we can say that the current through the resistor is 1.35 amps, and the voltage across the resistor is 5.7 volts. This means that the resistance value R is going to be equal to 5.7 volts divided by 1.35, which is 4.2 ohms. The last part of this section of the question asks us to calculate the total resistance in the circuit, and of course that's got to include the internal resistance. Sometimes it's useful to pull out part of the diagram again, so I'm going to draw the three resistors. As you can see, they look as if they're going to be all in parallel, but they're not, and the reason they're not is because there is a cell in series with the top one. Therefore, we have two resistors in parallel connected to a third in series. So let's deal with the parallel ones. Well, we know the parallel formula. 1 over RT is going to be equal to 1 over each of the two values of resistors added together. So 1 over RT is 1 over 2 plus 1 over 4.2. Therefore, 1 over 0.738 is equal to 1 over RT. So RT is going to be 1.35 ohms. So we can replace the two dotted resistors with 1.35 ohms. Therefore, we have the internal resistance and the load resistance like this. The load resistance being 1.35 ohms and the internal resistor being 1.5 ohms, which of course are connected together in series. So we can just add their two values together, and that comes out as 2.85 ohms. In the second section of this question, we are asked to consider the chemical energy that's converted into electrical energy in the cell and compare that to the energy used up over the three resistors. And we're going to do this for power. We know that power is I squared R. So the next session really asks us to just go through each of the components, calculate their I squared R power, and then add them up. So we start off with the internal resistor, and you can see you get 4.2 squared times 1.5, 26.5 watts. Moving on to the 2 ohm resistor, this is going to be 2.85 squared times 5.7 volts, which comes out as 16.2 watts. And then for the bottom resistor, 1.35 squared multiplied by 5.7 again, which equals 7.7 watts. Now, if we add those together, we get a total power of 50.4 watts. The very last part, which I haven't shown here, then asks you to think about the power generated in the battery and prove or show that energy is conserved. Well, we can't use I squared R for the EMF part of the cell because that bit has no resistance. So this time we have to say that the energy supplied by the cell is going to be equal to voltage times current. Now, of course, I do mean the energy per second here, or the power. And that is going to be equal to the 12 volts times 4.2 amps, which, unsurprisingly, is 50.4. In other words, we've shown that the power supplied and the power dissipated are the same. In other words, conservation of energy is proved in this question, and we can all sleep easy tonight. Well, I hope you found that, again, another helpful question. It's surprising how many students get stuck on that one. Please don't forget to like and subscribe, and why not drop me an idea for a question that you'd like me to look at down in the comments below. Thanks for watching. See you next time.